Good afternoon and welcome to our Vic Gardner webinar, Dispersing and Milling for Energy Storage. Today we have Andreas Stummer, and as it says, Andy is our Director of Dispersion, Sales Dispersion, and is very knowledgeable on our dispersion line. And he's going to give a presentation today, and permitting, we'll ask some questions at the end. If we don't get to the questions, we will always get back to you. We are recording this webinar, so you will get a recording afterwards that will be emailed to you. We also post them on our special YouTube page for dispersion, where you can find that there. And with that, I'll turn it over to Andy to start the presentation. Thank you for joining us today.
Thank you, Sherry. Hello and welcome, everybody. Appreciate you joining me today for a 45-minute little overview on technology that is used to disperse and mill slurries that go into batteries or fuel cells. So when we dive in, just a quick overview. So first, we're going to just give you a quick introduction into modern energy storage, a couple of slides. And then with this, we dive into the dispersing and milling process, how it's done. And then we're going to talk at the middle of the presentation about different types of equipment that we have for lab space, pilot, and also production equipment for these applications. And finally, we're going to talk about the lab resources that we have here in the US at Big USA in Wallingford. As you can see right here on that picture, it kind of outlines it pretty well, kind of the product line. So we start with very small units and we can go all the way up through pilot and then to manufacturing. Of course, there's even larger units that are not on this picture, but you can already see these units are used as dissolvers as well as basket mills. So these are all fully exchangeable. Okay. So basically, you know, everybody knows there's a lot of research that's being done with lithium-ion batteries, and this technology is always improving. And the goal is to increase the range, you know, have more power, shorter charging times, make them safer, and so on. So a lot of companies today are, you know, looking at that type of equipment, not only from an R&D perspective, but also from a manufacturing and scale-up perspective. So picking the right dispersion milling technology, also the additive package is really critical when we formulate these next generation, you know, slurries and battery designs for these energy storage systems or fuel cell applications. So solid state lithium batteries are something that is being worked on aggressively as we speak. So there's a lot of companies developing barrier coatings and so on, you know, that use our technology to just improve the performance and just help out, you know, developing the next generation batteries. And so we here at Big Gardner with VMA, who are the manufacturer of the equipment, offered really a good portfolio of products that help you develop these type of batteries or fuel cells. And the equipment really is designed to give you best performance, offer modularity. That means, you know, we can use them as dissolvers or media mills, depending on what you want to use them in the process, or how you want to use them in the process. So they can be used for grinding, mixing, homogenizing, and other, you know, dispersion requirements that may come up. And we work very closely with Big USA, they are the additives manufacturer, for this end-use market of fuel cell and battery. And so if you have questions on the additive side, I can also lead you to the right person. And we also have a lab up in Connecticut with Big USA where we can show the equipment and also help you pick out the right additives for your application. So, you know, the equipment is used for many different applications. You know, we have silicon dispersion requirements, electrodes, silicon oxides, lithium, polymers, solid state ceramic, solid state carbon graphite, carbon nanotubes, carbon black. So these are just some of those formulations that require really good dispersing technology. So when you look at, how these batteries are designed, so it's basically an electrolyte in the battery, and that allows the ions to flow in between the anode and the cathode. And they can be either liquid or solids. Soluble salts, acids, and bases can generally also act as these electrolytes. So dispersing and grinding equipment is used to, improve and develop these separators by helping to reduce the particle size down to primary particle size. And that will help then also with the transfer efficiency of these ion particles moving in between the anode to the cathode. So anode and cathode slurries are developed using a lot of our technology today, and that will help you get a better battery performance. So we also need to look at, rheology and viscosity measurements are often critical during the R&D or even manufacturing process to understand what's happening with the slurry while we disperse or mill. So we have also technology that can give you really good live data, and we'll talk about that helps you understand how is your slurry changing during the dispersing and milling process. And obviously, battery and fuel cell slurry preparation and processing measurement is also a key to really have a successful upscale result when we go from laboratory scale all the way up to pilot and then to manufacturing. So we have also a lot of that capability built in to our control panel. Here you can see this is a brand new dispermat developed for fuel cell and battery applications that has already a torque measurement sensor built in to give you this real good live data on viscosity that you might need when you develop your slurries. We'll talk more in detail about the different dispermats later down in the presentation. So here's just a quick slide about that torque measurement sensor. That is an optional module that you can acquire. It's basically not a calculated value when we measure the torque. We actually measure it. So we don't use the frequency inverter to calculate it. We really have a sensor that plugs into our shaft, and it has a very tight accuracy of 0.1 Newton meters. And all the data will be displayed on the actual control panel that you can see how is your viscosity shifting during the dispersion and milling process. So of course, torque value is an indirect measurement of viscosity and can be very helpful in understanding how well you're processing your material. So that's just one of the new developments that we offer with the TMS sensor. So then here's just an example of, an application where we did some cathode processing with the Dispermat AE. So obviously we add all these different ingredients, and then this is a container that is jacketed. We also have a cover to allow to purge with nitrogen or argon gas if that is required, so more like in a dry environment, and remove any type of moisture. So we did a really good job with that design, and it's very effective from a scalability point of view. So with that C technology, the control board allows you to really precisely monitor and control all the different variables such as speed, energy input, torque value. You can actually see the tape speed. We have a timer function and a temperature measurement built in that really gives you accurate data. There's also the ability to see everything, all the dispersion process in a graphical interface. So each of these variables, your speed, time, temperature, torque, energy input will be displayed in a graph, in a form of a graph with each of these indices as a trend line. So as you're dispersing and milling, and let's say your viscosity is increasing, that means you will put in more energy. Then if you're running with constant beat, then you should see a spike when increase in the trend line of your torque curve, for example. So that is really helpful to give you real good live data. Here is a good example of how we were able to really do a good job with that AE unit to reduce the particle size of a cathode slurry. So we used the Dispermat CN20, which is a standard middle of the road Dispermat with a Cowles blade for about 1 hour. So we're de-agglomerating these larger particles, and that starting point was about 100 microns. And then we were using the TML mill, which is a basket mill attachment that will pop onto the disperser head, and then basically it converts the CN20 disperser into a CN20 media mill, which is very unique to our approach to dispersing and milling. You only need one piece of equipment that can do both dispersing as well as milling. But the final result after 3 hours is really good. We were able to reduce the particle size all the way down to 2 microns on average. We are able to go much lower. We have a nano kit, but this is something that the customer wanted to see, and that was kind of their reference point. They were stopping the exercise at 2 microns, and they were very happy with these results. So leading into now the dispersion process, what are we actually doing when we use this type of equipment? So as you look under the microscope, a lot of times you have these clusters of particles. They are clumped together by this invisible, they're called van der Waals forces. They're basically like electromagnetic forces that bind these particles together. And our goal is really only to break up the binding forces. These larger clusters are called agglomerates. And by using a Cowles blade, a disperser with the blade with teeth, we're able to turn them down into the aggregate size. So these are smaller clusters with less particles, but they're still clumped together. If you want to go from the aggregate level down to the primary particle level, then you need to do milling. So that's why we have a basket mill or horizontal media mill approach to really help you reduce the particles down to primary particle size. And then, of course, we always need to remember that we need additives to help us stabilize our materials in the suspension so they don't flocculate back together. So this is a nice slide kind of laying it out with more pictures. So we start out with the Cowles blade on the disperser. We do some wetting and de-agglomeration of the larger particles. And when we reach between 10 to 30 microns of particle size, is kind of a threshold, is when we really start the milling process. You can see there's a rotor on the top right, the picture, and that will give us more shear force than a Cowles blade because we are using media, zirconium oxide beads with the rotor, allowing us to really take these larger, the aggregates down to the primary particle size. And then again, really critical is the stabilization of our particles in the slurry, where we need to use some formula to help us do that. So here is just a slide, again, how we were processing some material. This was for a ceramic separator application. And in this case, you can see the basket mill is inserted in the pot, and we have cooling jackets. So it's very important that we are properly cooling during the milling process. And then we use some Leponite RD from Big USA, the additive for wetting and dispersing. And basically, we're also put in to help us process this material. You can see on the bottom, I apologize, I'm not the additive expert, but I can help you, I can put you in touch with my colleague, Erin Kelly from Big Additives. She's really knowledgeable and is our end-use manager for the additive side to help you, guide you in the right direction. So this slide is kind of important because it lays out at what point we're starting to the milling process. So first you use the dissolver, and then anywhere between 10 to 30 microns, as I mentioned earlier, this is kind of a rule of thumb, is when we start the milling process. So we can use different bead mills We have a basket mill approach, what you've seen in the pictures earlier, works really well, or horizontal bead mills for super small particles, size requirements. Anything less than 500 nanometers, we need to use a horizontal media mill. And with that, we can really go down to sub 100 nanometers. We have customers that are milling in the 50 nanometer range with that type of equipment. So for pre-dispersion, it's really critical to remember when we use a cow's blade, we want to stay within 18 to 25 meters per second of tip speed. So that's kind of optimum, and that really yields really good results. So for that, we have a range of different disper mats we can talk about down a few slides later. I'll show you some of these models. And then we also need to remember when we are when we are milling, some people refer to it as fine dispersing or grinding. Our tape speed is between 10 to 16 meters per second, so a lot slower than doing the pre-dispersion process when we are milling. And there again, we have vertical bead mills. Our system is called the APS. We have also the basket mill TML, and then horizontal bead mill RS for manufacturing, or the SL for lab and pilot scale. So when we are pre-dispersing, the first thing that we need to look at is our container to blade ratio. That's really important. So depending on the viscosity of my material, I need to pick the right diameter blade. We always want to start out with about 1/3 blade diameter to vessel diameter range. So here you can see the picture. This is about 1/3. But for example, if I have let's pick a 1 liter, 1,000 milliliter container, you can see I can go all the way up to 70 millimeter blade, all the way down to 30 millimeter. My sweet spot will probably be in the 50 millimeter range. But depending on the viscosity, we need to maybe increase or decrease our blade diameter. That means if my viscosity is really low, I want to use a smaller diameter blade. If my viscosity increases, it gets really thick, more like a paste, I want to increase the diameter of my blade, help me move my product more. Imagine if you have a very thick slurry, almost paste-like. If you use a small blade, that would be very difficult to process the material because the blade kind of would be sitting in the middle of the container, kind of spinning and not doing much, while the product would settle out around the smaller blade. So therefore, it's really important to use the correct blade diameter for your viscosities. And there is a rule of thumb. So when you select the right blade size, when we talk about viscosities, we process materials from 0 to 500. We consider that low viscosity. Medium viscosities from 500 to 5,000, and then high viscosities anything over 5,000 centipoise. Just helps you kind of select the right diameter blade. So this is a really important slide. As I mentioned earlier, the tape speed is so important to dial that in correctly. So there is a formula. Basically, it's the RPMs multiplied by pi times the diameter of your dispersing blade. And then if you want to express that in meters per second, you divide everything by 60. But you have to also remember that the diameter of the dispersing blade also need to be expressed in meters. So if you have a 50 millimeter blade, for example, you need to express it as 0.05, and then times 3.14 times the RPMs. Let's say you're running 5,000 RPMs, and then you would divide everything by 60. That will give you the actual tape speed at 5,000 RPM with a 50 millimeter diameter blade. And the goal is to be, again, between 18 to 25 meters per second to optimize the pre-dispersion window. And when we are milling, 10 to 16 meters per second, but the calculation is the same. That's really important. And we have something called the donut effect. The donut effect is something that is called that way because it really is something that you can see when you look inside of a container and you're optimizing the dispersion parameters. So here we have the optimum tip speed, the right blade selection, a good viscosity. So here we see that there is a donut forming. That is basically the visual cue that, yes, I'm deagglomerating. This looks good. Should see good results after about 10 to 15 minutes. So that's what you want to see. Of course, there's going to be instances when you have really low viscosity materials where it's very hard to see a donut because the donut would collapse before it can even be formed. That doesn't mean that you are not dispersing properly. It just means you have very low viscosity. So you can play around with maybe a different blade diameter. But usually the donut is visible between 2 to 5,000 centipoise. You'll have no problem to see a really good looking donut. Now, here is kind of like how the donut effect is established. So you can see the blade has these teeth, and these teeth and the edges of our blade are actually causing the shearing. And this is where we are deagglomerating. And that's basically where the donut should build up. Right there on the edges, as you had seen on the slide earlier, is how we are actually getting to form a donut. This case, this was not a battery slurry here. It's actually a paint, but it's kind of same application. You get the idea. What's happening with the donut. So here you can see a really good donut, 21 meters per second of tip speed. So that's really optimum. And we are putting in about 850 watts of energy. So this looks a very optimized slurry. Beautiful. Now in this case, I'm also running at 21 meters per second, but I'm only putting in 320 watts of energy. So here is a couple of things that you can try to change that. You can see the slurry is kind of splattering around, and I'm not really seeing, a real donut. So it could be that the viscosity is too low for the donut to form, which I think is the case here because we're not putting in a lot of energy. So you could do two things. So either you change your formula or you change the diameter of your blade. So that would probably help put more energy in, or you can pump up the speed a little bit. But basically, these are the two approaches that you can take to maybe put in more energy and get a better looking donut. In this case here, we're running with 900 watts of energy input. We're also 21 meters per second. It's not a problem. We are putting in a lot of good energy. We don't see a donut because the material is really thick. So it has a very hard time to actually form a donut. So doesn't mean we are not pre-dispersing. It just means that our viscosity is probably quite a bit higher than 5,000 centipoise. Therefore, you're not really seeing the donut, but you are still deagglomerating. I would not be worried about it. So it's very important to remember that timing is everything, of course. So the duration of our dispersion, usually when we pre-disperse, as low as 15 minutes, as long as an hour, depending on the material. The donut effect is a good visual cue to help us understand how well we are, performing. And then tip speed, again, 18 to 25 meters per second is optimum. The geometric consideration, meaning the blade diameter, there's different blade types as well. Some blades are also with additional teeth, or they can also be different types of materials. That will also depend then on the viscosity. As I mentioned earlier, larger blades for high viscosities, smaller blades for very low viscosities. The volume of our mill base in the container, so we are looking at about 50% fill rate, as high as 70% and as low as 40. But 50 is kind of the sweet spot. We don't want to go too much higher because if you put in a shear, you're going to spill the material. Also, when you're milling with a basket mill, if you have a 70% fill rate, it's likely if you turn up the mill that you might have, because the basket mill weighs a lot, that it kind of pushes the product up, and then you could also have spilling if you go above 70% fill rate. So we like to stay in the 50% range. type of formulation, obviously, how much loading I have, the filler concentration. We want to keep the temperature as low as possible. When we're dispersing and milling, we're putting in a lot of energy. That energy turns into heat, and we need to really cool our mill base to stay below a certain threshold. And that's why we are using jacketed vessels or jacketed basket mills or jacketed horizontal media mills to ensure that we can properly maintain a workable temperature. And then again, additives, very important. Don't forget the good additive package to really help us not only process the material, but also stabilize it post-processing. And then once we are done with the pre-dispersion, which we move over then to the bead milling process. So, of course, bead milling is a whole different animal. It allows us to really now start to take the aggregates to bring them down to the primary particle size. A dissolver is great. We need it. It's an absolute must to start the process to de-agglomerate, but we can only put in a limited amount of energy, and it's really only used to de-agglomerate. And we cannot get to from the aggregate level down to the primary particle size with just the dissolver blade. But it is critical that you always start with the dissolver for wetting and for breaking up these large particles, because if you don't, you run the risk of clogging a mill, because the particles are so large that if you use a screen in your media mill or a dynamic gap, they would clog very quickly. So it's really important that you always start out with the dissolver. And then once we achieve good results and we are between 10 to 30 microns of particle size, is when we start the bead milling process, where we can put in a lot more energy. This really helps us to get down to the primary particle size and even nanometer range for a lot of these applications. And it gives us a much better looking product, much better performance, particle size is reduced, and also we have a much better particle size distribution. So what actually happens inside of a bead mill? So basically we have an enclosed chamber. It's open on top. It's not totally enclosed, but where the beads are. And then basically we have the slurry go in, either in a horizontal setup or a basket mill setup. And then inside of that mill, we have beads with our milling disc or rotor. So as these beads collide at very high velocities, they're actually pushing away these particles, these clusters. And that shearing motion, that action is actually what's causing the particle, the binding forces to break up and reduce the particle size. So that's really what is happening inside of a mill. And that's how we actually get down to the primary particle size. So kinetic energy is very important also to remember. There's a lot of people that talk about different types of beads. We have customers, most of them use zirconium oxide. They are very good beads. They're heavy. They will much higher kinetic energy than, for example, something like glass or light beads. So kinetic energy is very important, and beads play a really important factor in that. As you can see, M, weight of the bead. So if you want to write down the formula, that helps you understand how much energy you're putting in during the milling process. So this kind of slide here shows it well. The difference, for example, you have a zirconium oxide cerium stabilized bead. The specific gravity is 6.1 versus a glass unleaded is 2.5. So it's almost 2.5 times heavier on the weight per bead. Also much harder. It's almost 3 times as hard to use a zirconium oxide bead than a glass bead. So yes, they're more expensive, but they are really the right media to use when you're milling these types of slurries. So there's all different sizes available depending on the final particle size that you're looking for. We usually start out with our mills at about 1 to 1.2. That's kind of like where we start with a 0.5 millimeter mesh. And then also a dynamic gap in the horizontal mills, standard 0.3 millimeter that allows us to use the 1 to 1.2 millimeter beads. Okay. So this is Good slide. I like it because it kind of shows you again. You have these larger um, beads, and then right in where these beads merge or collide together, right there is would be your particle cluster, and then that would be pushed out. That's the shearing happens in these corners as the beads collide, where the breakup of the van der Waals forces actually takes place, and continuing to reduce the particle size during the milling process. So it's not so much that we're always crushing the particles. Think about it this way. When you were a little kid and you sat in the bathtub and your mom gave you a rubber duck, and you tried to grab the rubber duck in the water by pushing your hands together. What happened? The rubber duck, you probably didn't get the rubber duck, right, in the water. The rubber duck was always pushed away by the force from the water. And that's kind of like what's happening inside of a bead mill. So the beads would be acting like your hands, and the particles would be the rubber duck. As the beads come together at high velocities, that rubber duck or that particle cluster would be pushed away, and that pushing motion, that shearing force, is enough to break up the binding forces and make the particles smaller. Of course, excuse me, you can also crush some of these particles, but the idea is to break up the binding forces, and you're really achieving that through those shearing motions, and that's what happens inside of a bead mill. So here are some of the critical parameters that are going to influence our process. So particle size after pre-dispersion with the dissolver. We talked about that earlier, 10 to 30 microns, kind of the sweet spot. Bead size, depending on how small you want to go, what is the final particle size, but we like to start out with about 1 to 1.2 millimeter. Specific weight of the beads, really important to bump up the kinetic energy. The bead loading, so that's kind of fixed depending on the type of mill that you're using. Shape of the beads, very important. You always want to get really good quality beads. If you look at them under the microscope, they should be perfectly spherical and not oval shape or edges or something like shards. We have seen all sorts of poor quality media at low cost from low cost suppliers that do not hold up to good standards. So make sure you spend a little bit more money on better quality beads, but that will be very helpful in the process. And please stay away from glass or anything like that, as glass will break easily, and then you end up with shards in your mill base, and that is not good. Speed of the milling tool when we're milling, again, 10 to 16 meters per second. I know I'm repeating myself, but it's really, really important to maintain a good tip speed. Product temperature, again, control is key. We have cooling jackets on our supply vessels as well as on the milling chambers. How often does it go through the milling chamber or basket mill? The total amount of milling time. How long does my product sit inside of the milling chamber? If my milling disc speed or my rotor speed is low, my pump speed is low, obviously it takes more time to travel through the mill. So you need to dial that in to optimize for your viscosity and to have really good processing of your slurry. That is the next part is the viscosity of the mill base. When we are milling, it's important that we always have flowability of our material. If we can't have a slurry that flows, then we can't really process it well because it will not go through the mill. It gets stuck like a paste, right? So if I'm using a basket mill, it would just go into the container and would just sit there, and the product wouldn't get inside of my mill. With a a horizontal bead mill, it's a little bit easier, but still difficult to process non-flowable materials. You can use some sort of a plunger system, so we actually force it through the mill and out with pressure. That is also not great because you're gonna have stuff getting stuck in there that's not milled. So always try to dial in your formula so that the material at least has some flowability. My test is always I have a container with your product, I turn it upside down. What happens to the product? Does it come out? Is it flowing out? If it's flowing, even as high as honey, as long as it flows, I can process it. If it's stuck in the container, it's very difficult to process. Okay, so that will severely limit the type of milling system that you can use for that type of formula. So now we talk a little bit more in depth about the different types of dispersion units we offer. So one of the key things I mentioned earlier is our modularity approach. So you have a standard dispermat, which is the piece in the middle, a dissolver, and then you can accessorize it depending on how you want to work with the equipment. So it gets delivered with a blade, but then you can buy a rotor stator, a vertical bead mill, a wall scraping unit. We also have a vacuum system called CDS, and the TML basket mill are all components or attachments that you can buy later on to put onto our dispermat. The way that this works is we have, as you can see on this picture, right below the motor on top, there is a clamping ring. You can kind of see that. There's what's called a DL shaft. And the DL shaft functions almost like a bayonet style system. So you remove the clamping ring, you turn this assembly 180 degrees, and it will pop out. So you can just pull it down. And then you just replace it with any of these attachments, and you put it in, lock it back in place, put on the clamping ring, and now you're running a basket mill, for example. That is really cool because you don't need to buy multiple pieces of equipment. Everything can be processed on one machine. You just buy the different attachments. The vacuum system is nice because it allows you to not only pull a vacuum, but I can also purge with nitrogen or argon or any other inert gas if that is critical for your process. I can also acquire a basket mill with vacuum capability also. So that means not only can I disperse under vacuum, but I can also mill under vacuum, or if I don't need vacuum, mill with nitrogen or argon or any other inert gas as well. So that's really cool, and that is unique to the VMA dispermat line. So here is a better picture. Actually, I should have shown it earlier. You can see the clamping ring right up here below the motor. That's what you remove, and then you kind of turn this assembly 180 degrees and pull it out and replace it with whatever attachment you want to use. So this one comes with the torque measurement system, has the ability to add vacuum. We have the ability to also have variable speed. Obviously, we can also run the machine not only with a certain speed, but also with constant power. That means instead of running, let's say, 3,000 RPM, I want to run this trial or manufacturing process at, let's say, 3,000 watts of energy. Then as my viscosity changes during the dispersion or milling process, my speed would adjust. So if my viscosity is increasing, my speed would decrease because I'm maintaining the 3,000 watts of energy. If my viscosity decreases, my speed would increase because I'm maintaining the 3,000 watts of energy. So that is called constant power. So I can either go with constant power or constant speed, depending on how I want to run it. Or if I want to go from small lab scale to manufacturing, I might want to use constant power because it gives me really good quality upscale data. And not only is it easy to process the material, but it will also help to calculate how much energy you would be using to process a certain amount of material in a certain amount of time when I'm using constant power, because I know exactly how much energy I'm using. Again, the modularity approach with the various accessories. Again, we have customers that used to do planetary mixing, and they kind of move away from that because it has limitations in particle size reduction capability. So they like this system where you can just add on a basket mill to really bring down the particle size. And then we have, of course, explosion-proof options available. Software for the higher end models where you can download the data to an Excel sheet, upscale data available. So it's really helpful. The C technology is kind of our bread and butter platform for data processing and how we run the dispersion and milling process. A little bit about the motor technology. So our motors, if you ever worked on a dispermat, you would recognize it immediately because they're so quiet. They are basically beltless, direct drive motors. So there's no maintenance on the motor at all. So the shaft plugs in right to the motor below. There's a flange that goes directly into the motor, so there's no belts or anything like that. No oils needed, no grease. So these machines will last a lifetime. We have customers that are using Dispermats that are 40 years old that are still running on the original motors today without ever having to do any maintenance on them. And they're workhorses, so they're extremely reliable and high quality build. Then we have a very cool unit. It's for dispersing slurries under a vacuum. So this is the vacuum dissolver, purpose built. So this is not a modular attachment. So this is really built that way. And it also comes with the wall scraper. So a lot of customers really like that option to remove the slurry from off the container wall and push it back into the middle. And that's what that little arm does. That's, you can see that in the back there behind the blade. That would be actually the dispersing or the scraper blade. So the cover is open on top. I mean, it's closed, but you have the ability to open it with a viewing glass. There is a light, so you can see what's going on inside of the container while you're pulling a vacuum. But again, vacuum is not a necessity. You can also just purge it with nitrogen or argon gas or any inert gas that you would like, and then you can process your material that way. Cooling jacket, so this is double walled and has all the pressure gauges on top. And then we have the ability to supply with one base model, different size containers, so you don't have to swap out the cover. So as you can see, there's a container behind on wheels that's smaller than the one that's locked in place. That container, though, has a collar on it. That collar perfectly fits the cover of the VL. So that means it's fully exchangeable to different container sizes depending on how much slurry you want to process. So very cool, very good to go from small scale to manufacturing, because we also offer vacuum dissolvers for manufacturing also. So this is the latest dissolver, very small lab scale. It's called the Dispermat CV3 Evo, and it's going to be released here in May. We're going to actually have it. We had it down in Florida at the battery show, and we're going to have it up in Detroit, Michigan. I think it moved from Novi to Michigan to Detroit, the large battery show. So we'll have one of those up there as well. So this can go up to 20,000 RPM. We have the ability to do, full attachments on here, dissolver blade, TML basket mill, APS vertical bead mill, vacuum system, or even a rotor stator would all fit onto this machine. Beautiful design. And the premium model, there's going to be two models, a basic model and the premium model. The premium model also has the ability to plug in a scale on the control panel right next to it, so you can weigh out your raw materials right next to the dissolver, and it'll show the data on the screen right here. And then you can store all the data for different batches, so you can give a batch a name or a product ID, and that way next time if you want to download all the data, you have all the data right there, as well as all the raw materials that you weighed out on your lab report. So very cool. Then we have the CN. This was the model earlier I showed you, where we processed the cathode. Just a basic machine. Has also the ability to put on all these different attachments. And then we can go pilot scale in the same model range, in the CN range. Again, very simple, high quality build, giving you excellent performance for larger volumes. Then we have the AE, which is kind of our premium line, also with the AE RE for batteries. So this is fully expandable again, but it has that C control panel. And again, this is also scalable, where we can go up to an AE pilot unit for larger volumes. Again, this can all be configured for vacuum or argon or nitrogen. And then basically you also be able to mill with this machine also, not only disperse, but you can add a basket mill on here, as you can add on the smaller models. Then we have a range of horizontal media mills that are used to go into the super, super small nano range. So anything less than 500 nanometers, as low as 50 nanometers. We can do that with the SL machine. So on the left, you have the lab model. And then the production scale. One example of a production scale would be the RS on the right. So in our lab in Connecticut, in Wallingford, we actually have an SL up there with the nano kit. So if you ever want to come up there and take a look or run your slurries, you're more than welcome to join us. Here's a little more information on the production side horizontal mill. Again, we have ceramic capability. We can add a nano kit. We have vacuum option. So many different configurations that can be picked to meet your requirements for your application. And then we move into a little bit of a production scale overview. So here is the Dispermet SC. We can go up to about 2,000 liters of product volume. Again, we have the quick change system, that bayonet style, where we can move from a dissolver to a basket mill on one machine. We also can add a wall scraper. We can do the vacuum or nitrogen upgrade, all available with our production scale equipment. This slide kind of shows you have the SC, and then with the quick change, you just quickly go from a dissolver over to a basket mill. Again, the advantage there is I have one machine that can do both dispersing and milling, so I don't need to buy two machines. So it's very, very nice to process the material in a very, ergonomic kind of way, in a space savings kind of way. You don't need to have multiple pieces of equipment. We use a trolley to actually replace the dissolver shaft with the basket mill back and forth. So that changeover can take about 5 minutes and is really quick and effective. This is what it looks like with the vacuum option. So you kind of see this is a vacuum cover with all the different ports on it. And again, that vacuum is only an option. It's a sealed container. So again, we can do the nitrogen or the argon or whatever inert gas you want to use. But it's really effective. We have different control panels, C technology or M technology, depending on how much data output you want to get from your production unit. Vacuum is also helpful in a lot of cases. It takes out foam. So during the dispersing process, sometimes if you don't use a defoamer, foaming can be an issue, especially transferring product from one container to another. So that way we eliminate foam and just apply the vacuum. And then we have a really cool system. It's the Dispermet TM. Quickly, this machine is cool because it already combines the basket mill and the dissolver all in one. So you don't have to change anything. So you first pre-disperse your material with the cow's blade. When you're ready to do milling, you push a button on the control panel and the basket with the cover comes down, and now you're milling. So you don't have to move containers around. You don't need to use a second machine. So everything can be done on one machine in one real process. Very well streamlined design and optimum for companies that don't want to move product containers around from one system to another system. Everything can be dispersed and processed on one machine. So that's what it kind of looks like. So pre-dispersion, fine grinding, giving you really excellent results. But this is only good for up to about 500 nanometers. Anything smaller, we really need to use a horizontal mill like the SL or RS I showed you earlier. Easy to clean, very safe. And again, space savings are huge. And it's a 2-in-1 machine. Very cool. This is actually two Dispermet TMs not in action, but in installation mode. So we have a very large container. It's actually 2,500 liter container back there. The blade, the cow's blade, is actually leaning against the gentleman. The guy with the gray sweater behind him is a blue drum, and that's where you can see the blade. He's leaning against the blue drum. So that blade is not installed yet, but you can see the basket mill right below the cover. That would be our basket that contains the beads and the milling disc. And the disc format on the right is the same model, except here it's still collapsed. It hasn't been raised up yet, but that's what it kind of looks like during the milling process. So the whole thing comes down, and then the cover closes the container, and then you are milling. So you kind of see the height of the system during the milling process. So you don't have to take off the blade when you're milling, so everything stays on there. You just push a button on the panel, and then you are milling after you're done dispersing. Really cool system and extremely quiet. We also offer explosion-proof models as well. Here you can see a close-up of our basket mill. The nut right here is used to basically close the hole for the bead filling. So here is actually a funnel that you would put in here, and then you add your beads to the milling chamber of this beautiful TML basket mill. Fully jacketed, it's double walled, so we have cooling in on the right. You see that bar, and then on the left, cooling out. And then we also have a third bar in the back that you can see a little bit in the background that holds the basket, but it's also used to measure the temperature. We measure temperature inside of our basket, so that is very, very cool. APS system for milling, very small volumes. This is for lab scale. It's basically 2 containers. So I have a milling tool that I put on my dissolver shaft, and then I have a container. The top one has my slurry. When I'm done pre-dispersing, I add beads, and then I basically on the mill in a closed system. It has a cover, and there is a drain plug on the bottom in the screen that's right above the drain plug that separates the beads from my slurry when I'm draining my material. There is a air socket, a socket that I can plug in an air hose. Now that is cool because when I'm done milling, I will remove my drain plug, but to speed up the purging process, I can now apply air or nitrogen or anything I want, and I can purge out my material with pressure into the container below. That is really effective in smaller volumes, but not really good for large-scale manufacturing size batches because you have 100% bead loading. If I have, let's say, 1 liter container, I can use 500 milliliter of slurry and 500 milliliters of beads. So I have a very high bead volume with the APS, giving you excellent milling results, but not good for manufacturing because imagine if you have 2,000 liters, you cannot have 2 tons of beads. First of all, it's cost prohibitive, and how do you handle and clean the beads? Very difficult. So this is excellent for lab scale. Just 2 different control mechanisms for our manufacturing capability. We have the C technology on the left, very simple control panel on the right, very manual, no data tracking, but very functional. Then we have a lab in Germany. That's a picture right here at VMA-Getzmann, the manufacturer of these beautiful systems. If you have a sister company or you want to go over there to check out the equipment, let us know. We can set that up. You're more than welcome to even run your material free of charge and evaluate the equipment. In the US, we have a beautiful lab in Connecticut. In Wallingford, we have a lot of high-end equipment in there. We have that horizontal SL mill, and we have also a Dispersing AE. Unfortunately, I don't have the torque measurement sensor, but it can still measure torque with the frequency inverter, but you get the idea. We have a lot of capabilities up there. Also milling capabilities, basket mills, and so on. And then finally, one slide from the additives group about the different additives that they offer for your electrodes and your separator coating, so they can help you there with the defoamers, wetting, and dispersing additives to give you really good results. And my colleague there is Erin Kelly, and she would be more than welcome to help you out. So Wallingford site is a first-class laboratory facility for dispersing, applications. It's also a battery additive development center. energy storage solution processing technology center. So we have everything under one roof. And basically the idea is to have customers come in to evaluate the equipment and then also basically run trials and help you really understand how well does the equipment work with your for your application, and then also help you with scale up. And the good news is we can really leverage our synergies between the instrument and the additive business, making, giving a customer not only support on what type of technology, but how do you have a better formula. If you don't want to run product and just come in and look at the equipment, you're also more than welcome. And then we can also do training and use it as a seminar location for customers. With that, I think this concludes our presentation. We did for 55 minutes, and I'll open it up to 5 minutes of questions.
Thank you, Andy. That was very informative. I'm just waiting to see if there's anybody putting any questions in, and we will get to those. I think you did a great job of discussing how not only is it wonderful technology to really get the job done and find solutions, but there's several options that, VMA-Getzmann's really taken into account. The fact that, most items are interchangeable, or you can just add something to it that you don't have to go buy a whole new device, and you can do multiple different processes.
I see, Sherry, you posted a link to the YouTube page. Mm-hmm. We'll upload that presentation on there. You can also see a walkthrough through the lab. If you want to come up, please let us know. We'll be more than happy to set that up and bring your material in, and we can run it and process it. So show you the value and the performance.
And as Andy also mentioned, we will be at the Battery Show in October in Detroit. We will also, if anybody would happen to be at the Coding Show, we will be at the American Coding Show at the end of this month with our instruments there. Oh, I do see a question. How's your RS horizontal bead mill compared to the Netsch Profi maybe systems? I'm not sure if I'm saying that correctly.
So that's a good question. So actually they're very similar. I think they're both for wet grinding. The layout, I think they have what's called a Profi. It's very similar. There's one, I think they make one for pre-grinding as well. So we don't have pre-grinding really. I mean, depends. Some people call it pre-grinding. I mean, you can do very large particles. You just have very big media. Then you got to come down. But the design is actually very similar.
Thank you. I'm glad that we were able to answer your question.
And Salvador, if you want to visit us in the lab, we can do a trial for you and show you on the SL. The scalability is excellent, and you get a really good idea of the performance of the mill.
And if anybody has any other questions, we do have a couple more minutes if you want to get those in. If not, you're always welcome to, email back to any of our emails that we send. We will always, get back to you. Those all tend to come into me, and then I will forward them to Andy or Jonathan, our business line manager. We do have a presentation coming up on May 7th, a webinar on the new CV3 EVO that Andy mentioned. And then also May 14th, we go into more deep dive of dispersion and medium milling in June. So lots of opportunity to continue learning. If you do need, any assistance, as I said, you can always reach out to us. Anyway, covered everything so well today that there aren't a whole lot of questions right now.
Must be that we explained everything so well. Okay.
Yeah, I'm not seeing anything, so I think we'll let you get back to your day. And as mentioned, you will get a recording if you wanted to review that again and share it with any of your colleagues. Or as mentioned, reach out to us and we're happy to help you, get one of these instruments into your facility.
Thank you, everybody.
Thank you, Andy.